So this section, even though there's nothing really new in it, is very, very important. So all of these integration techniques that you've been studying, the new ones from 8.2 through 8.5, it's easy maybe to work on them when you're focused on that one strategy in that section because right, this section is about partial fraction decomposition. So I know I'm going to use partial fractions. What's harder is when you get all of these integrals together and you have to choose what strategy to use. So this is a really important section. I encourage you, I know I gave you some suggested ones, I encourage you to do more. Just like anything in mathematics, you gotta practice. It's training your brain to kind of see different ways to do things. And the other thing with this is you have to understand that sometimes you're going to make mistakes and you're not always going to pick the right way the first time that you try it. Right now, I've been doing this a long time. I've been teaching for like 15 years. I've taught Calc 2 lots of times. So, it's easier for me to see some of the things that are going to happen, and you would want that because I'm your teacher. But also realize that sometimes I try stuff and it just doesn't work. So I'm actually doing these. I picked these out because I think I know what to do with them. I haven't actually done these examples. I have 3 examples for you. 3 examples? I think 3. And if I make a mistake, I make a mistake, and that'll be all right. So let's look at this one. So what you want to do with these integration strategies, you always want to try and do the simplest first. So by simplest, really what I mean is substitution, because that's going to be, the most basic method that we have besides just outright being able to take the antiderivative. And it's important to note that I can't take the antiderivative of this as is. I can't just go inside and take the antiderivative of these 2 and then add 1 to this and divide by it. Don't make things up, right? We know we can't do that. So what I'm going to do is I'm going to try a substitution. Now I know this might be a little tricky, but really what this is crying out for is, u equals 1 plus e to the x. Now, what are some of my other methods I could use? I could use maybe a trig substitution, but remember, trig substitutions involve a squared minus x squared plus a squared, and to where I could maybe get a substitution to get to there. And maybe this will become a trig sub, but I doubt it. Parts doesn't look really easy right now. I don't have 2 things multiplied together. I can't take the antiderivative of it. If I try and make that u, that's going to be a difficult derivative. The other thing you cannot do, and some of you did this on the test, and it made me so sad. Oh, so sad. You cannot distribute exponents over addition and subtraction. Please just don't do it anymore. It makes me so sad. You can't do that with square roots either. Guys, you can't do it. So stop doing it. Okay, good. I'm glad we had that talk. I feel much better. So what I know, this guy's going to be replaced by u, but I know I need to get rid of that dx also. So now du in this case, right, is e to the x dx. So if I were to solve this for dx, now what you want to be careful of right here, and I've mentioned this several times, is we don't want to have 2 variables in the integrand. So the only reason that I'm going to be able to do this is because if I look at this part right here, I know I don't want is that a pentagon? I know I have 2 variables here, but I think I can mess with this a little bit, right? And so how could I mess with this? Well, this e to the x right here, let's solve this for e to the x and see what we get. So we see that e to the x is u minus 1. I don't know if this is going to work now. I think it's going to, but I'm not totally convinced. But let's see what happens then, okay? And I think what I'm going to do is I'm going to right now just ignore the definite integral, and I'm going to see if I can find an antiderivative just with the indefinite integral. That's a trick I'll use if sometimes I don't want to worry about the bounds, because I think some stuff is going to happen with this u substitution where I might have to do more stuff to it. But I could change the bounds too if I want to. For now, though, I'm going to just look at the indefinite integral. So let's see what we get here. So I'm going to get the integral of, this is 1 over u squared for sure. And then what is this dx right here, right? Well, what is it going to be, what is it going to be replaced with now? Well, what this, because of that e to the x is actually u minus 1, that e to the x I'm going to rewrite as u minus 1. So what is dx going to be replaced with? It's going to be replaced with that 1 over u minus 1 du. Okay, and so this is why we're going to, it looks like we have a partial fraction decomp. Yes, love partial fraction decomposition. It's so much fun. Okay. And now this is something I can work with, right? I got to remember, I got to bring that u back in eventually, and I got to worry about my bounds eventually. But for right now, and I might even change my bounds here. I might go back and put my bounds on here. Who knows? Who knows? But what I need to figure out right now is I need to figure out how to take the integral of 1 over u squared times u minus 1. This is begging for partial fraction decomposition. I have a factored polynomial in the denominator. I don't have something like u squared minus a squared or a squared minus u squared, so I can't do a trig substitution. So now I'm just going to focus on doing a partial fraction decomposition. So let's do that over here. So I have 1 over u squared times u minus 1. So let's look at the factors that I have. U squared, that u, right, in here is linear. And it's a repeated linear factor. So we need to put 2 of them. So remember, with the repeated linear factors, we put 2 of them. I'm going to multiply both sides by u squared times u minus 1. So I get 1 equals, so for a, one of the u's will cancel, and I'll just be left with u times u minus 1. For the b term, my u squared will cancel, and I'll be just left with u minus 1. And then for my c, the u minus 1 will cancel here, and I'll be just left with u squared. Now this one I can't really do the trick of, I mean I could let u equal, 0 and u equal 1, but I won't be able to get all of my variables from that. So what I'm going to do instead is I'm going to equate coefficients. So if I take this au through, I'm going to get au squared plus au. Take the b through, I get plus bu minus b, and then plus cu squared, and then I'm going to combine like terms. So my squared terms, I have a plus c times u squared. My u terms, I just like to underline them to make sure I've considered every single term, and then minus b. So I'm saying that this polynomial 1 is equal to this whole polynomial over here. The only way for that to be true is if there are no u's, or excuse me, no u squareds on each side, no u's also. So I'm going to set a plus c equal to 0. I'm going to set a plus b equal to 0 because I don't want any u's either. My goodness, Sarah. And then I'm going to set that negative b. I do want a constant. I want that constant to be 1. So if I look at here, this implies that b equals negative 1. So that's one of my solutions. Here, this is going to, if b is negative 1, I have a minus 1 equals 0, which implies that a is 1. And then if a is 1, 1 plus c, if that is 0, that tells me that c is negative 1. So that green was like a little, this is the stuff behind the curtains that I want to see. But clearly then we come down here and we say, all right, I'm picking up back where I left off with that equals sign. And this becomes, all right, what is a? A is 1. So I have 1 over u. B is negative 1, so I have minus 1 over u squared. And c is negative 1, so I have minus 1 over u minus 1. Du. Oh my goodness, I'm kind of glad I didn't change my bounds. I'm going to just deal with this and then we'll come back. So let's start taking antiderivatives. So the antiderivative of 1 over u is the natural log absolute value of u. Antiderivative of 1 over u squared. Don't put the natural log of u squared. That doesn't make sense. This is u to the negative 2. So what is its antiderivative? You need to do a little bit of side work. It's a negative u to the negative 1, but this negative actually makes it positive. And I'll just put that as 1 over u. And then here, if I did like a w substitution, because I've already done a u substitution, we'll see that we just get the natural log of u minus 1 here. And the nice thing is because the derivative of u minus 1 is just 1, that's why I don't really have to do u substitution. I'm not going to be off by anything. And I could put a plus c here, but remember what I'm trying to find is the antiderivative to put into a definite integral. So I'm actually not going to worry about it. All right, I'm coming all the way back up here. What was u? Guys, I barely remember. What was u? U was 1 plus e to the x, and we're going from 0 to natural log of 2. So 1 plus e to the x. So I have natural log. I don't need my absolute values anymore. Remember, e to the x is always positive, and 1 is always positive. Wouldn't be wrong to put it. A little redundant, but not wrong. And then here, if I put 1 plus e to the x minus 1. Oh, guys, this is cool. Look at what I'm going to get here. So my 1's cancel. The natural log of e to the x, remember those are inverse functions of each other, so they cancel. Or another way to think of what is the natural log of e to the x is to watch how I raise e in order to get x. Well, I would raise it to, in order to get e to the x, I would raise it to the e to the x. Or those kind of cancel. They undo each other because inverse functions, when we compose them, undo each other. Oh my goodness, I already forgot what my bounds were. 0 to natural log of 2, right? 0 to natural log of 2. This was a great one. 0 to the natural log of 2 of 1 over 1 plus e to the x squared dx equals, remember, fundamental theorem tells me, hey guys, you just need to find an antiderivative. I have found one antiderivative, namely with the constant being 0. So natural log of 1 plus e to the x plus 1 over 1 plus e to the x. Again, you may do this differently because you may have decided to change your bounds. And then if you had changed your bounds, we wouldn't have had to come back to that 1 plus e to the x, but I don't really need those there. All right, so let's start plugging this stuff in. So I get natural log of 1 plus e to the natural log of 2 plus 1 over 1 plus e to the natural log of 2 minus the natural log of 2 minus this whole thing with 0 in it. Don't just assume, don't assume. We know what assuming does, right? Don't assume that 0 is going to make everything go to the 0. It doesn't, especially when we're dealing with exponential functions, right? We got to be a little bit careful there. So let's simplify this. We don't want to leave it like this. We wouldn't get full credit for it. So this guy right here, e and natural log of 2, remember they cancel each other out. So this whole thing right here actually is just 2. So I get the natural log of 3. Okay, over here again, that means this is 2. So I get natural log of 3 plus what, 1/3? Natural log of 2 I can't do much with. E to the 0 is 1. So I get minus, again, the natural log of 2. And e to the 0 is 1. So that'll be minus 1/2 if I take that negative through. And then that 0 is 0. And then, I don't know, we could simplify this a little bit. We could do natural log of 3 minus 2, natural log of 2. There are 2 of those. Oh, 1/3 minus 1/2, I think, is a 6th. Negative 6? That'd be 2, negative 1/6. And that's my exact answer, right? So anytime I ask for the exact answer, that's what we want. We could find the approximate answer of it, too. Wow, that was awesome. You guys, let's just take a moment to appreciate that. Look at that. That was lovely. Go scare your friends with that. All right, let's do a few more just because I think that was a good time. So what about something like this? This one's similar just in that I'm going to start with a substitution, and then after that, I don't know. Okay, I can see that I'm going to do a substitution here, and then I'm not exactly sure what we're going to do, but I kind of know. I think we'll be all right. So let's look at my substitution. So, you know, I'm taking the cotangent cubed of e to the x, and then I have another e to the x out here. So that guy's kind of just begging for me to let u equal e to the x, and du its derivative is sitting there. So, I mean, that makes me really, not obvious, but it helps me to see that if I just let u equal e to the x, its derivative is already there, so I get the cotangent cubed of u. And now this is a trigonometric integral. So we got to figure out what we're going to do with cotangent. So what are some things I know about cotangent? I know that cotangent squared plus 1 equals cosecant squared, right? I know another couple things. Let's just kind of write down what we know. We know the derivative of cotangent is a negative cosecant squared. Ooh, that might be helpful. I know the derivative of cosecant, I don't think this is going to be helpful, is a negative cosecant cotangent. So I need to somehow get this cotangent cubed to look like one of these. And I think the key is going to be, I don't think I know, but I think the key, wow, it's going to be this guy right here. Because if I solve this for cotangent squared, now let's think about this a little bit. If I solve this for cotangent squared, I realize I have cotangent cubed, but if I solve this for cotangent squared, I'm going to get cosecant squared minus 1. I don't know if I want to do that, but I'm going to just try it. So I'm going to try it. This is good, right? This isn't embarrassing at all, that I'm not quite sure what to do here. But let's go ahead and take off one cotangent. And let's, so I'm going to rewrite cotangent cubed. I'm not going to do dw. That's just going to confuse you. I'm going to take off one of the cotangents, okay? And I'm going to rewrite that cotangent squared, because you know what, you guys, I'm not having any luck with the cotangent cube, so we might as well bring some cosecants in here. Because if I bring some cosecants in, maybe the math gods will smile upon me and allow me to do something with this, right? And now that I see this, I see I'll probably be able to do something here. Let's break this up. Let's break this up. We'll have cotangent of u times cosecant. I see the x now, my fault. Cosecant of u du. And then if I take that cotangent through, I would have minus the integral of cotangent of u du. Now the integral of cotangent of u I will give you, but another, I believe that's one of those, right, that I said I would give you in 8.1. But if you don't see that, cotangent of u is actually not too bad to figure out, okay? Because cotangent I can rewrite as cosine of u over sine of u, and that's what I can do with that, and then I can do a u substitution. Even here, I have cotangent u cosecant squared. What I'm going to do with this first one is I'm going to do a u substitution, but instead of u's, because I already used it, let's use w's. So I'm going to do a w substitution. So what will I let w be? I'll let w be cotangent of u. So what is dw? It's a negative cosecant squared of w, of u du. So that's going to work great. I'm going to be off by a negative, so this will be a negative dw equals cosecant squared of u du. And then again over here, I'm going to rewrite cotangent. Let's use a different color here. If you don't know this, let's just look at, I'm going to rewrite cotangent as cosine over sine. I'm going to let w in this case be sine. And the reason that's going to work is because its derivative of cosine is just sitting right there. Oh, we're cooking with gas now, people. All right. So what do I have here? This is replaced with w. This cosecant of u du, right, is replaced with a negative dw. So I'm just going to put that negative out front. Over here, right, I have my w in this case is sine of u, and its derivative is just sitting right there. So I have 1 over w dw. And we're almost, and I probably should have used different w's. Let's call that w sub 1. W sub 1. There we go. So in this case, I get a negative 1/2 w squared. Over here, I get negative natural log absolute value of w sub 1. And then this is all plus c. And now we have to come back. So what was w? My first w was cotangent. So this will be cotangent squared of u minus the natural log of w sub 1, which was sine. So this will be sine of u plus c. But remember, I didn't start off with u's. What did I start off with? I started off with x's. And what was u? U in this case was e to the x, right? Whoa. Whoa. Come on. Come back. So what is my final answer? I know that took a while. It did. And it would probably take you a little bit longer maybe than it took me. But I have faith that you can do it with enough practice. We're done. Just like that. Look at that. That was a great one. I enjoyed that one immensely. All right. All right. Let's look at one more. One more. And we're at 17 minutes. One more. These, I can show you lots of examples, but the ones you do in your homework and the ones on the fun sheet are going to be different in these examples. So it really is just going to be a matter of you working on these. Tangent squared theta d theta. All right, guys, so I have theta times tangent squared. I think when I look at this, I want to try an integration by parts. But here's the problem. If I do integration by parts, I usually want u to be theta. I want that to be like it's something whose derivative is more simple than it, right? And then what would that leave me for dv, though? dv would be tangent squared theta. I don't know, maybe I could do this, d theta. But it's going to be difficult for me to easily, yeah, we could probably do it this way, but it's going to be difficult for me to easily find its antiderivative. So I actually am going to change this up a little bit. The other thing is if I let u equal tangent squared, right, then you have chain rule going on. Don't forget chain rule. You have to bring the 2 down, leave the inside, take the derivative of the inside. Ugh, right, that's too much. So what I want to do is I see that I have tangent squared. So what do I know about tangent squared? I know that tangent squared theta plus 1. Sometimes this is what I'll do if I'm not sure where to go, is I'll kind of just write down everything I know about that trig function that I have and see if something cool pops into my head, which sometimes cool things pop into my head, but a lot of times not. What about the derivative of tangent? I know that I think this is going to do it, guys. I know that the derivative of tangent, right, is secant squared. So while I think parts is still going to come into play, I think I can make my life a little bit easier. I don't know. I think I could have still done parts from here, but I'm going to rewrite tangent squared as secant squared minus 1. Okay, and I'm going to break this up now into 2 separate integrals. So I'm going to take the theta through to each term, and then I'm going to consider, don't forget you can consider these integrals separately, if you break them up. Now you need to make sure you have good notation, right? Notice that I'm doing a d theta with each integral, right? But, this isn't too bad because I know I can figure that out. That's 1/2 theta squared, right? What about theta secant squared? So let's look at that one. I'm going to try I'm going to try parts, because if I let u equal theta, that leaves for dv secant squared d theta. That's a good thing, because remember, I want to pick a dv whose antiderivative is easily accessible, right? It was something that I can easily find the antiderivative of. So in this case, du is d theta. And then in this case, I can just see, right, the antiderivative of secant squared is tangent. That's great. What a fun one. All right, so what do we got here? So I'm going to take u times v. So uv, sunny voodoo, right? uv minus v du, the integral of v du. So I'm going to do uv, there's theta, tangent theta, minus the integral of v du. So that's tangent theta d theta. And then I'm going to just go ahead, I put an equal sign, guys, so you best be equating. And I'm going to actually just wait to put that c because I still have this integral to take, and so I'll deal with that in a minute. Now, the antiderivative of tangent, that's what I'm going to give you, but if you don't see that one, antiderivative of tangent actually isn't too bad. The trick with tangent is to rewrite it as sine over cosine. Okay, look at, I'm having good notation. I'm putting in the equal sign. If I let u equal cosine of theta, du then is a negative sine of theta d theta. Okay, so I get theta tangent of theta. Now this becomes a plus sign because of that negative right there. Integral of 1 over u du. Not being lazy, I'm carrying everything down with me, and we are almost done. So we get theta tangent of theta, okay, plus the natural log, absolute value of u, but in this case, what did I let u be? I'm going to go ahead and go there. Cosine of theta, absolute value, minus 1/2 theta squared. And now we're just going to add all the c's together to get one big C right there. And we're done. So, that was like 25 minutes of, for only 3 examples. These can get pretty tricky. They give you really good advice in your book. Consider their advice. Think about the ways that you can integrate. Substitution, trig subs, trigonometric integrals. integration by parts, and you got to try stuff. Don't be scared to try things. Sometimes it's not going to work, and that's okay. That's okay. Let me know if you have any questions.